Brilliant. Yeah, so when they asked me to give a talk, I was really nervous. I said, but I've never worked with Jim. And then I thought about it, and you know, Jim's been a major part of my career. He's been a mentor, a friend, a guide, and somebody, I think we all have our heroes in science, and Jim has definitely been one of mine. So thank you guys, it's great to be here. So when I first met Jim and his group was at a Mona Symposium in Jamaica, and at that meeting you can see some people who are perhaps in the audience here, not Paul Rees, who was the organizer of this meeting and organized many more of these wonderful natural products meetings. There's Jim there, very young Jim, Adam, who is here in the audience, and also Bernie. And the person who took the picture was Helen, and so that's the empty chair there with Helen. So that was a wonderful occasion, and I got to know them all very well. Following that, Jim and I did organize a meeting together at Furbush, and this is one of my favorite photographs. I have this photograph in my office, and here at the front you can see some of the leaders in the field at that time, including who I did my postdoc, Jake McMillan, many others here who you'll recognize, I'm sure. But also what I love about this picture is the future leaders of the field. There's Helen, Alicia, Nick, Sabina, a very young David O'Hagan in the background. And so I think that's lovely to see the evolution of science in that picture. So, as we've heard in these wonderful presentations today about the research in Jim's group, and it truly is interdisciplinary. He obviously collaborated a lot with Peter, and together they push the boundaries of science. And really thinking about biosynthetic pathways, but much more of that, enzyme structure and mechanisms, isotopic labeling, really honing spectroscopic methods, both in NMR and mass spectrometry. And we've heard quite a lot about tetranacin, nothing yet about erythromycin, which I thought was interesting. But anyway, so juxtapositioning molecules, you're absolutely right. Whenever we read journals, we get so many acronyms. This is one that I came up with for Jim. And if you look at the definition of it, it's placing two things together with contrasting effect. And so I think these pose is, sorry Helen, is a lovely demonstration of that. You can read the body language. I don't need to say anything about it. But when you bring those two things together, be it molecules or people, an interaction can create a change. And I think you can see the obvious change here. And I think that typifies Jim. He was so much fun. It was always great being at meetings with him. He'd bring a lot of humor as well as support to everyone. So what about juxtapositioning in molecules? We've heard a lot about enzymes. They're huge molecules. You can take a big molecule and a small molecule, and they look completely different. But clearly, if we bring them together, they can do something really exciting, as we've heard in many of these lovely lectures so far today. And in this particular case, what they've done is cyclized into an incredible 3D structure, and you can think of this as molecular origami. Thanks to the presentations of Ulf and this morning of the presentations that we heard, we know the importance from Rich and from Finian of biocatalysis. It really is becoming increasingly important in sustainable synthesis. Global market now about $7 billion. But over 10 years ago now, Reitz actually wrote, there's an urgent need for biocatalysts for carbon-carbon and carbon heterobond formations. And of particular importance are reactions which might be difficult to do easily in a chemical laboratory. And that got us thinking about the Diels-Alder reaction. We've heard quite a bit about this so far today, a 4+2 cycloaddition, in which you can generate up to 4 new stereocenters in a single pot. So we began to read the literature, and there's greater than 400 natural products potentially biosynthesized by Diels-Alder reactions, and many groups have made contributions to this. And unfortunately, I don't have time to acknowledge all their work today, but really there's some lovely, lovely work out there in the literature. So thinking about the Diels-Alder reaction takes us as a link to Finian's talk about thinking about tetranates, which are these 5-membered ring lactones. Finian's already told us a lovely story about tetranacin, which involves a heterodiels order reaction. And he alluded to some of the compounds we're interested in, which are these spirotetranates, where the tetranate is actually bound to a cyclohexene or a derivative. And there's a large ring, which could be carbon 11, 13, 15. But we're going to focus here on abyssamycin C. Now, it may not be immediate obvious. How is a Diels order reaction involved in the biosynthesis of this molecule? But if we do a retrobiosynthesis, where we cleave the carbon-oxygen bonds, takes us back to a cyclohexene, and then this linear molecule with a tetranate. Now, the two ends that need to react are quite far apart, but you can envisage bringing those close together to enable a 4+2 cycloaddition. So what controls these enzyme-catalyzed Diels order reactions? And importantly, can they really be used in sustainable synthesis? So there's two stories, if I get time, I'll tell you about abyssamycin and tetradecamycin. Abyssamycin C was first isolated from Micromonospora. It was collected here off the coast of Japan. Very potent antibiotic, and it exists in two atropisomer form, where the carbonyl is towards you or away from you. Many studies have elucidated the biosynthetic pathway, which is a typical polyketide pathway in which we have a heptaketide assembled from 2 propionates and 3 acetates. This is released from the acyl carrier protein to form the important 5-membered ring, and then further tailoring leads to this substrate for the key Diels order reaction, which does the molecular origami to make this rather interesting structure. So let's focus in on this particular reaction. And it was reported in the literature this is likely to be catalyzed by an enzyme known as ABYU. So ABYU was recombinantly overexpressed in E. coli, and it's a lovely enzyme to work with. Even chemists can work with this one with no trouble. And as part of it, we also needed substrates and potential products. And so Nick and Alex developed a total synthesis of abyssamycin C. And as part of their strategy, it was to give substrates for the enzyme as well as potential standards for HPLC. And here's the X-ray structure of, it's actually atropabyssamycin C, of that lovely structure. I think the folding pattern is beautiful. But what this gave us were the substrate and the potential product from the ABYU catalyzed reaction. Then we could use HPLC to follow the process. So here's a synthetic reference. If we heat that for 2 days, 70 degrees C, you can conduct the Diels order reaction, giving a product. But with the ABYU catalyzed reaction, is complete in less than 30 minutes at room temperature. Now, you might be saying, well, hang on, are you sure the enzymes involved? We know Diels order reactions were promoted in water, but if we use denatured enzyme, there clearly was no reaction. So to gain insights into this process, working with Paul Race's group, and we've had a long-standing collaboration now, the crystals were grown, the structure was determined, and in the active site, basically what's happening, the two ends of the molecule are being brought close together, and then working with Mark van der Kamp, who's a real expert on computational methods, we could begin to appreciate the difference between the abyssamycin C and its atropisomer. So if we look a little more closely, it's an 8-stranded beta barrel. It's dimeric in structure, but importantly, it requires no cofactor, and it's really easy to use. It's completely stable, warm up to 60 degrees, it's no problem, and we've been able to undertake mutagenesis experiments. And for those who aren't into enzymology, I often think of these beta barrels which are involved in Diels order reactions, a bit like wheelie bins. So what you've got in a wheelie bin is a base, which is our salt bridge here at the top. We've got a lid, which opens up, which is a capping loop. And then we have the active side, which is mainly within the bin, and it's largely hydrophobic in its nature. So it really is looking like a very promising catalyst for use in synthesis. For example, we can simply remove these methyl groups. Of course, that's now an achiral molecule. Incubate it with ABYU for about half an hour, and it folds up beautifully. And as you would expect with an enzyme reaction, and importantly for enantioselective synthesis, it gives a single product by HPLC. Now, where we're taking this now is to immobilize the enzyme, and that's working well, and popping it into flow so the reactions can be scaled up. But there are a myriad of Diels alderases potentially out there in the literature. One that attracted our attention was the one producing abyssamycin 2 from a Streptomyces. Same series of sort of processes. We've determined its structure, and we've looked at it in vitro assays. But what's really interesting here, the substrate is slightly different, and this was synthesized by Sabru, and Catherine did the protein work, and then together they showed that this folded up to this molecule. So if we look at the two enzyme catalyzed reactions, in the case of ABYU, this is folded up through this sort of conformation, giving the R stereocenter at the spirocenter, whereas with the ABMU, we have the S stereocenter. So effectively, it's like they're the two enantiomers which are being created there. So I'd now like to move on to the second part of the talk. And following Jim's retirement, it was really lovely. On occasions, there were a gang of us who would meet up in London, and we would talk about anything and everything under the sun, but in particular, the future of science. And as Helen said in her introduction, Jim might just take an opposite stance to you. Now, I love organic synthesis. And he would be provocative, saying, oh, it's dead, you can't do any more organic synthesis. So I do want to share with you our most recent total synthesis, and this is of another natural product, tetradecamycin. Now, this was first isolated from Streptomyces strains in 1995, and it was mainly its bioactivity which attracted scientists. At that stage, there was a real problem in Japan with yellowfish being infected with this pseudotuberculosis, and it was having a dramatic effect. And a particular molecule that was isolated, tetradecamycin, seemed to be active against this infection. Well, some 10 years later, a new metabolite was isolated, a huge job. An enormous amount of solid agar was used to get 1.2 mg. If I'm honest, we got attracted to this structure just because of the structure. Isn't it lovely? It's a tetracyclic structure. It's got a transdecalin with 6 contiguous asymmetric centers, a tetranate which is bound here through a 7-membered ring oxygen heterocycle. Could we make it and supplement this 1.2 mg for biological assessment? No formal biosynthetic studies have been done on this molecule, but it was by the Canadian group, the biosynthetic gene cluster has been identified, and by analogy to other tetranates, it's proposed that this is the biosynthetic pathway. The key is a Diels order reaction here, possibly catalyzed by TED-J by homology to other Diels alderases. Then from there, you can envisage epoxidation, cyclization, would give our target 13-deoxytetradecamycin. So we embarked on the synthesis of the racemic material based on our knowledge from the biomimetic potential, taking this aldehyde, coupling it with a tetranate. It's proceeded no trouble. But we could not do that Diels order reaction. We tried heating it, a range of Lewis acids, it would not work. And one of the possibilities is that we've got 2 dienophiles here. So let's step back to the simpler molecule. Then the 4+2 cycloaddition proceeds well to give the aldehyde. Then you could add the tetranate. Then the synthesis was completed in 3 further steps through epoxidation, demethylation, and cyclization. So the question really is, and it goes back to really what Manfred Rietz said, you need to be looking at reactions which are difficult to perform in the lab, and we certainly found this one very difficult to perform. Would our enzyme, TED-J, actually affect that required transformation? So TED-J, like many of the enzymes which produce decalins, is a flavor enzyme. It was recombinantly overexpressed, and we did the in vitro study, taking the starting material here, incubating it with TED-J for about 3 hours. It cyclizes beautifully to give a transdecalin with 4 new stereocenters with complete control. And again, importantly, it was a single enantiomer. The structure of this didn't come easily. Catherine, who was doing this work, worked for over a year to get this structure out, but we now have a better feel. And again, what's happening is in the active site, the molecule is being contorted, as shown here. And because, again, it really doesn't need any cofactor, it's very easy to scale up. And so starting with this tetranate here, the Diels-Alder reaction catalyzes cyclization, giving a single enantiomer, then an epoxidation, which needed to be selective, demethylation, and cyclization yielded 13-deoxy-tetradecamycin, and was the same in all regards to the natural product. So I hope today I've reflected some of the work and some of the inspiration that certainly Jim has given to me in terms of combining chemistry and biology. And it's not just Jim, there's been others over the time in the natural product world who I'm really grateful, not least of whom is Jake McMillan, who was my postdoc supervisor. So I hope I've shown by gaining insights, we can actually provide new catalysts for use in organic synthesis. Well, sorry. So finally, oh, it doesn't like that slide. So finally, well, sorry guys, my gang will not be happy with me. You're not allowed to see them. But I would like to thank Jim and all my group for all the hard work they've put into this. It makes it sound easy in a talk. They work so hard, and it was a great pleasure to interact with them. I'd like to thank the people who fund the work, and I'd like to thank you for your kind attention.